Welcome to Models 2020 conference on model-driven language engineering and systems. My name is Eugene Siriani, General Chair of the Models Conference, and I'm accompanied with my colleagues, Huari Sahrawi, Co-General Chair, Juan de Lara and Silvia Abrao, who are the PC chairs. This is the first edition of a virtual Models Conference. Unfortunately, due to the global sanitary restrictions, we don't have the chance to host you here in Montreal this year. We hope you're all staying healthy and enjoying the conference from your home or office, wherever you are in the world. Nevertheless, we hope to have you in Montreal in the future very soon. Since you can't come to Montreal, we wanted you to have a glimpse of the beautiful weather we had this weekend. This is taken from the balcony of my house. And this is the weather now. And actually, this is the weather since Monday, so maybe you haven't been missing much. So the organizing team behind this edition of Models is composed of my colleague Huari Sahrawi and myself as co-general chairs, Juan de Lara, who's the program committee chair of the foundation track, and Silvia Abrao, the program committee chair of the practice and innovation track. And our right hand, Sébastien Moser, who is running around like crazy as virtual conference chair. We, of course, couldn't organize all the events and the multitude of satellite events that happened in the past 3 days without the help of our 32 organizing committee members who volunteered for their task. So we thank them all very preciously. Also, we thank special thanks to the steering committee who helped us take the hard decisions this year, especially given the circumstances we are living in. And if the conference is running smoothly, it is thanks to our 16 student volunteers who are working behind the scenes, making sure everything is in order and you are in the right sessions and everything is working smoothly. We thank the sponsors and supporters of Models for their financial aid that had allowed us to keep the registration fees at a bare minimum. As you have all witnessed, it is a record minimum, these prices this year. In particular, we thank the Association for Computing Machinery, the Untitled Chapter, the IEEE Computer Society, the TCSC chapter of IEEE, the University of Montreal for the institutional support, and our two sponsors, our silver sponsor, Inquiry Labs from Hungary, and our bronze sponsor, the Institute of Valorization of Data, IVADO, as bronze sponsor. Some of our sponsors have a virtual exhibition booth that you can directly go visit in Wova, such as the one of Springer and the one of Inquiry Labs. We invite you to go and talk to them and see what they have to offer. Of course, the conference cannot happen without you all, with an overwhelming record of attendance of all times of Models, with 500 participants as of this morning. And since then, I know we're already at 503. But this is an overwhelming number, and we thank you very, very much. It's much appreciated with all the support you're showing us. We did not expect that of a high number, and we're really happy to have you with us. So all of you participants are coming from 40 different countries. And for the first time, Canada has the most participants with almost 100 participants, followed by Germany, who's the highest after that. And we also have a lot of participation from France, and we have seen a good rise from the US. We're very happy to have them also here. We also have a lot from the UK and the usual suspects from Europe. You will notice also that Japan also has a significant amount of participation. We're very happy to have them. And we have less common attendees from less popular countries at models, and we're very happy also that they joined, such as Brazil, Cameroon, Uruguay, Algeria, United Emirates, Saudi Arabia, etc. We're also very happy with as you can see, there's a good balance of participant profiles. So half of the participants come from academia as professors, researchers, postdocs. 27%, almost a quarter, are students, typically master's or PhD students, and a good 21% are from the industry or practitioners. And so we're very happy to see a very healthy balance of the different profiles. We're also very happy to count exactly 101 female participants. We're extremely happy for that. Actually, there's even on WUVA, there's a discussion forum called Women at Models, and it's quite active. So this is, we're very happy that this is happening. So the bottom line from these numbers is that you have all ample opportunities to discuss and interact with many people in the conference, and we really invite you to do so. The means are there in WUVA, so you can interact with anybody you want.
So we are proud to offer a very exciting program. So we had a very active 3 days, last Friday, Monday, and Tuesday, with 11 workshops covering many topics related to model-driven engineering. We had 7 tutorials, a doctoral symposium, educator symposium, and these 3 days. So we had 1 day yesterday, and we still have some activities related to industry days today, and a co-located SAM conference. We also have SPLC running at the same time with sharing the keynotes. We also have a very interesting technical program. My fellow colleagues, PC chairs, will give some details later on in this presentation. We will have a presentation from the SOCIM journal first paper. We will have also three most influential papers, and we will have 11 poster presentations. We are proud to have 3 outstanding keynote speakers. So Yohsua Benjio a little bit later today, Betty Chang and Christoph Zernecki. And the most interesting things, including the panel, is these people are covering our main theme this year, which is modeling in the era of data, and from different perspectives. So I encourage you all to attend this very exciting presentation. We will also have an award ceremony tomorrow after the keynote. As you have all noticed it, so we are using the WUVA platform to attend the talks, but also to network, to discuss, and to exchange. So there are some features, very interesting features, like having the agenda, but also looking who is there in the attendees, exchanging messages. We have a very active community section with many meetups, with live video chat possibilities. So we encourage you, if we want to have like a live discussion on a particular topic, to create these meetups. We have also some community topics, probably more than 40. You can start any group or social group. So this is open to all attendees. We also, thanks to our colleague Jörg Kinsley, we have a very exciting games and entertainment sessions every afternoon break. So the 3 session we already got was really, really funny. So don't hesitate to participate. You just click on the session every day, and you could read the instructions and participate in these games. This is a very good way, especially for newcomers, to socialize with people and have starting some connections. The proceedings are already available for the main track, for the main conference. So this is the link for the proceedings. You received an email about that. We also will have in a few weeks the companion proceedings for the workshops and all the other satellite events.
I will simply add a couple of points. So all the sessions are recorded, and you can find them all in Wova. If you go back to a session that already passed, just allows some time because we need to process the video before it's put up there, so you can have access to it through Wova only. And second of all, so each session you have a button called rate session, so you can give your feedback to the organizers of the session or the workshop or the tutorial, and we will make sure this feedback is forwarded to them. Starting tomorrow, we will start sending a post-conference survey, and we would really like you to fill it, because we want to have your feedback on the first experience, because it's new to everybody. You know, we haven't done that before, running a virtual conference, so we really need your feedback so that next editions that may require some virtual setup may build on top of this feedback. So keep your eyes on such an email. So, and with that, we will pass to the program committee chairs.
All right, thank you, Yin. Just a few words on the selection process in the main track. So as you know, we have two tracks at Models, the foundation track that accepts two kinds of papers, full papers, and then shorter new ideas papers. There is also the practice and innovation track that accepts more application-oriented papers, filling the gap between foundational research and industrial needs. To evaluate, we set up two committees, one program committee for each track, and then a common program board. And the role of this program board committee was basically to supervise the reviews, ensure the quality, foster discussions, and then try to lead to a consensus about the papers. As you have seen, we have used a double-blind process where neither the author's identities or the reviewer's identities are revealed to each other. And this is basically now the norm in most software engineering conferences nowadays. And the goal of this double blind is to make the process as fair as possible, to avoid either positive or negative bias if the reviewers would know the author's identities. To evaluate, we set up 3 reviews per paper, and in some particular cases, we added more reviews, and then 1 meta review, which was done by the program board committee member. And to give you an idea, altogether, we had more than 500 reviews with a total amount of more than 2,200,000 words, which you know is more than enough for a couple of novels. So the decisions were not only made based on reviews, but there were intensive online discussion using EasyChair, leading to more than 1,000 messages. And then the final decisions were made on an online program board meeting. So in the next slide, I will show you a couple of numbers about this year process. So I think this year, for the first time, Models gave a deadline extension because of the COVID situation. And despite the difficulties, we found a lot of support by the community, because we ended up with 142 abstracts, which materialized in 127 submissions. And this number is almost exactly as the number in last year, and even higher than in some previous year. So overall, we accepted 35 papers, which gives an acceptance rate of 27.5%. And in more detail, we received 87 full papers in the foundation track, and 2 papers were moved to the practice and innovation by recommendation of the program committee and program board members. Then we also had 21 new ideas vision papers, and considering these 2 papers that were moved, 21 papers in the practice and innovation track. Then for the accepted papers, there was an optional process for artifact evaluation. So basically, here we assess the quality of the artifacts that support what is written in the papers, and we thank the artifact evaluation chairs for that. And as you will see a little bit later, the program has also papers coming from 3 other sources. So the first one is the SOSIN journal that, as you know, is the main journal in our community, or one of the main journals. And we are presenting some journal first papers. So what does it mean? So these are papers that are not extensions of papers presented in conferences, but were directly submitted to the journal. And so we give them the opportunity to some of these selected papers to present the work in the community. So we thank Jeff and Bernard for this selection. We also have tools, because you know that tools are an essential part of our community, to support our automation, the automation that is inherent to model-driven engineering. And we thank the demo track chair for that selection. And finally, we have also posters reporting on last minute new research, and also supporting what is written in the accepted papers. So in the next slide, I will show you some numbers about submission and acceptance rates by country, which fits almost exactly with the participation. No? So we have the most active authors were from Germany, France, United States, Canada, and the UK. And you know, these countries have a long commitment in our community in the past. But you can see there are also other countries that are emerging to contribute more to our community, like China or Japan. If we look at the success rate that is given to you here by the gray portion of the bar, we have to mention that some countries like Hungary and Switzerland have a perfect score, but other countries like Luxembourg and Norway score very well this year. And with this, I will pass the mic to Silvia, that will tell you something about topics and how we organize the topics into the program.
Thanks, Juan. Hello, everyone. And now let me share with you some information about the papers. As far as topics submitted and accepted, what we are seeing here is a graph that gives you an idea about what the hottest topics are according to keywords used in EasyChair. Ours are related to model-driven engineering languages, modeling language, and metamodel, as well as model transformations, and a few others. But you can also see that there are other successful topics that indicates a tendency of applying modeling to emerging areas such as cyber physical systems and digital twin, but also established areas such as product line. Next, Eugene, please. So now concerning the most successful topics, according to titles of the accepted papers, we can see in this word cloud that the most successful topics were model-driven transformation, model-based, and so on, as expected. But a comparison of these terms used in the title of the papers suggested that the topics were more focused on transformations than modeling in general. The term generation was more used than model to text. Model-driven was more used than model-based, which is somehow aligned with the fact that transformation is one of the most successful topics this year. UML appear also a bit more than domain-specific. In addition to these terms, there were also other traditional topics that were frequently used in the papers, such as engineering, build, language, and automating. And finally, what is interesting to see is that security and robotic systems have emerged as application areas of special interest this year. Please, Eugene. Now, I will talk a little bit about the program. Overall, the technical program will be running for the next 3 days. We are going to host 15 live sessions in which the 35 accepted papers will be presented together with the 10 papers from the journal First Track at SOCIN and 15 demonstrations. In addition, as Juan already anticipated, 11 posters will also complement the program and will be presented in parallel with the live sessions. Actually, we have a very exciting program with high quality papers. In particular, on day 1, which is today, we are going to have 6 sessions on relevant and interesting topics, such as system engineering, model analysis and validation, and so on, that will take place in parallel right after the keynote by Yohsua Benjio. On day 2, please, Eugene, next one, thank you. On day 2, tomorrow at 10 a.m. after Betty Cheng's keynote, there will be an award ceremony where several awards will be announced, including 2 ACM 6 of distinguished papers and the best papers from the foundations and the practice and innovation track, and also best reviewer awards. Afterwards, there will be 2 parallel sessions on requirements in language engineering modularity. And after the panel, other 2 sessions on behavioral modeling and models and data, which is going to close the second day of the conference. On day 3, we are going to have also an interesting session on verification, testing, and execution, right after the keynote by Christoph Czarnecki. Then other 2 parallel sessions on modeling environments in model search and runtime and architecture. Finally, but not least, the sessions on safety, security, and testing and variability and evaluation will close the technical program. Before we finish, we would like to thank all the members of the team for their great support. We really appreciate it since this year's organization was particularly challenging. Really thank you all the PC members, additional reviewers, program board members, steering committee members, the virtualization chair, who is doing a fantastic job behind the scenes, the session chairs and student volunteers. Thank you for all the continued support that you have given to us during the year. Also thanks SOCIN and Springer for their support to the conference. To finalize, a quick mention about how you can interact with the presenters to ask them questions. Please post your questions as comment in the Zoom chat, and they will be selected by the session chair during the paper presentations. Also, we want to support open science, so we encourage you to publish a preprint of your paper and share the link at the model's website if you have not done it yet. Also, please don't forget to tweet about the conference using the hashtag ModelsConf. With this, we want to wish you a really great Models conference and enjoy the program. Thank you.
Just to mention that our keynote speaker is experiencing some technical issues. This should be resolved before 9:15. Meanwhile, just to mention that for the keynote, we will use the Q&A for the questions. So you can ask your questions using the Q&A, and after the keynote, I will look at the questions and ask them to the keynote. So sorry for this small delay. We should start the keynote in, I would say, less than 15 minutes. pleasure to welcome Yohsua Benjio as our first keynote speaker in the main conference track of models 2020. So Yohsua is a professor in the Computer Science and Operation Research Department at the Université de Montréal. He is the founder and scientific director of MILA, the Quebec Artificial Intelligence Institute, and of IVADO, the Institute for Data Valorization. Just to cite a few of the long list of awards and honors, he is the recipient of the 2018 Turing Award for pioneering deep learning. He is a fellow of the Royal Society of London and the Royal Society of Canada, and an officer of the Order of Canada. He has a tremendous impact on the research community and on the society in general. I'm not talking only about the number of citations from publication in almost all the research fields, literally. By the way, I counted that I will need probably many lives to have the same number of citations he got last year only, which is 87,000 citations, probably the highest number reached in research. I'm talking also about his effort to organize his research community as a member of the NeurIPS advisory board, as co-founder and member of the board of ICLR conference, and as a program directors of the CFAR program on learning in machines and brain, to cite a few. Perhaps most importantly, I have to mention his effort to push the limit of intelligence through learning, as well as to favor the development of AI for the benefit of all. In this respect, he played a key role in the elaboration and the promotion of the Montreal Declaration for Responsible AI that I invite you to read and sign. So Yohsua, welcome to our conference and to our community.
Thank you very much. Larry, do you hear me well?
Very well.
Thanks for the kind words, and sorry for the being late. I thought it was 9:30. Okay, so I'm going to tell you today about a research program that I've started the last few years, which is trying to go beyond some of the limitations of deep learning as we know it today. Deep learning has been amazingly successful in many areas, but if you compare the intelligence of the systems we have today with human intelligence, even of a 2-year-old, we see that there are some major gaps. And so what I'll tell you about is first trying to understand some of those gaps and how they might be interrelated, and how we can get further inspiration from human cognition in order to guide our quest towards better AI. Okay, so let me start by how I got into the field of AI and neural networks when I was a grad student, and I was looking for something to do for my master's. I started by chance reading some of the early neural net papers, including by Jeff Hinton, and I really got excited about those papers. And what excited me the most was this idea, which I now call the amazing hypothesis. The idea is that there could be a few simple principles similar to the laws of physics that could govern intelligence, and that could explain first human and animal intelligence. And then of course, if we understand those principles, then we could build intelligent machines as well. And for this to make any sense, those principles would have to involve learning, because the dominant thinking in AI in those days, in the 80s, was that intelligence was a huge bag of tricks, essentially, of all the pieces of knowledge that we have, and also tricks to do inference with those pieces of knowledge. Instead, the neural net and machine learning approach focuses on the idea that there are some pieces of knowledge that are like fairly simple and generic, how to learn in particular, that allow you to acquire the rest of the knowledge, or at least a large part of it, that humans acquire in their life. And so the actual specification of those principles can be pretty compact. That means that there's a chance for researchers to actually think of it like some formula that would govern how intelligent machines can become intelligent through experience. Okay, so that was the motivation. And in those days, the approaches that I learned in my classes, in my AI classes, were based on symbolic rules and logic. Knowledge, instead of being acquired, was provided by humans. But as I'll try to express in many ways today, there's an issue with this, maybe the central issue with that classical approach. And that is the fact that there is a lot of knowledge that is somehow in our head, but we don't have conscious, explicit access to it. It's not communicable. It's what you might call intuitive knowledge, like a lot of common sense, things we don't need or can't communicate with words. So if that's the case, and there's a lot of evidence from neuroscience and psychology that is the case, then how could we program computers to be as intelligent as us if we don't have access to like 90% of the information that we would like computers to have? So that the solution is learning, obviously, because that knowledge is something we could hope machines could figure out by themselves. If we can't give it to them, maybe what we can give them are the sort of guidelines. In my field, we call them inductive biases, like priors, that human brains may exploit, that help them make good use of the information that they're acquiring in their lifetime. So that was the motivation for machine learning. In addition, there were other issues with the classical rule-based approach, that not only there is no learning, but also there was a lack of handling of uncertainty. I mean, in the real world, very few things are certain. And you have to be able to handle that. You have to be able to manipulate that uncertainty, to predict under uncertainty. You have to think in probabilistic terms. And modern machine learning has put a lot of emphasis on that, so as to be able to deal with things like sensory data, where there's a lot of that uncertainty. Now, machine learning has been incredibly successful, but it hasn't yet addressed some of those objectives that classical AI was trying to address with symbols and logic. And so a large part of what I'll tell you about is how can we bridge that gap and address some of the cognitive capabilities that humans have and that early AI research was trying to duplicate with all this symbolic stuff, because that's also part of human intelligence and somehow is missing in current machine learning. So the neural net approach is brain inspired. It's about the synergy of a large number of simple adaptive computational units, which we can think of as neurons, maybe groups of neurons. And one of the central ideas that has driven my own career is that information is represented through what Jeff Hinton called distributed representation. So the idea is, instead of having a symbol that says cat, when I see a cat, what you would have is a pattern of activations. And the pattern of activations for, say, neurons in the brain, and the pattern of activations for cat would be overlapping with the pattern of activations for dog. So this is very different from the symbolic representations, because in the symbolic representation, cats and dogs have orthogonal representations. Like there's nothing in the way that the symbol cat that tells you that it has things in common with the symbol dog. You need extra information. but that extra information is something we can actually build in the representation. So those representations are learned, and they're learned towards some objective, like learning to perform a task. So if I go back to this question of principles, one of the framework that encompasses the large majority of what we do in machine learning and in neural nets in particular is build systems that have these three ingredients. There is an objective or reward function that is to be maximized, like minimizing errors or achieving some goals that an agent is trying to aim. Second ingredient is how we optimize it. Like this is an optimization method. It's a learning rule. How do we change the synaptic weights towards that objective? And the third ingredient is what we call in neural net jargon, the neural net architecture, or if you want mathematically, is what is the parameterization? What is the family of functions within which we're going to be doing the optimization and the search for good solutions to the learning problem? So that's the building blocks of most of machine learning. And deep learning, which is the 21st century version of neural nets that incorporated first the idea of having many layers of representation, has been very successful, especially on perception. So images, sounds, but to some extent, the progress has been also quite impressive on manipulating language. I mean, in my group, we had breakthroughs in terms of machine translation, which have very quickly been adopted by industry, and all of the machine translation systems that you can buy today are based on these ideas. And of course, playing games, many people have heard about AlphaGo, the system by DeepMind, which is beating the best human champions, something that was not thought to be possible for a long time. Now, this is good, but we are still far from human level AI, as I was saying. The machines we have today still have to be taken by the hand. You have to have humans providing the labels, providing the information about the high level concepts that the learner is supposed to acquire. Unsupervised learning, although it's an old subject, is something closer to what humans do, and in particular, the ability to figure out the appropriate high-level abstractions is something that is still missing in some ways, and maybe as a consequence of that, we see that the kinds of errors that current machine learning is doing are sometimes very, very different and very surprising compared to what human errors. So what you see in the slide here is on the left an image of a dog that is correctly classified, and on the right it's an image that has been perturbed very slightly, so you don't even notice the difference. But it's been optimized the change has been optimized to fool the classifier into thinking this is an ostrich. So when you try to understand what is going on here, what it looks like is somehow those current systems are relying on fairly superficial clues rather than really capturing the abstract dogness, if we want here. And so they can get fooled if you work on it. So at a theoretical level, one way to understand what is missing and that differentiates current machine learning from the way humans learn is the notion of out of distribution generalization. So what does that mean? The standard theory for machine learning assumes that the system we are training will be deployed under examples from the same distribution that gave us the training data. So, this seems reasonable. And if it was not the same distribution, then what kind of guarantees can we have anyways, right? But in real life, like for humans, we are in a non-stationary world, that things change, and yet we're able to cope with that. So what happens that has, industrial consequences is that the systems we train today, they work well if you test them on the same kind of distribution that you're trained on. But in the field, there will always be something different. Maybe you train on data from one country and then you test on data from a different country, and it doesn't work nearly as well, right? So one may ask, and today I'll try to dig a bit in that direction. How do humans manage to generalize out of distribution to somehow do a good job, even though the environment has changed? And one idea that I and others are exploring is the idea of appropriate knowledge representation. So what allows us to generalize in novel ways is, I mean, the new environment is not completely different. It reuses some of the concepts we already know. It's just that it reuses them in novel ways. So I'll get back to that. And so we need to think of, for example, neural nets that modularize appropriately, that separate knowledge into pieces, such that those pieces can be recombined on the fly based on the need. So here's an example of that. What you see on the right here is a new vehicle that maybe you've never seen before, but actually you can make sense of it because of other examples of vehicles you may know. And this is something very human, that we are able to make sense of new things like this that are very unlikely under the training distribution, because maybe this does not exist, right? So you don't see it. But actually, we can make sense of that. When I tell you a science fiction story, right, you can make sense of it, even though it might be very different from anything you've experienced. If you drive in a country where the traffic laws are different, somehow, even though it might be a bit painful, you can survive. And it's interesting to ask how we managed to do that. So researchers in the last few years have been trying to set up benchmarks where they evaluate how state-of-the-art machine learning systems, which typically are deep learning, behave when you change the distribution in those ways, where you expose them to new data that really concerns combining existing concepts in ways that they have not seen before, and maybe had even zero probability under that training distribution. And linguists have been doing this kind of, studying this kind of thing, because humans do that in language very naturally. Like that when I talked about the science fiction scenario, it's really a language thing. Like we can make sense of combinations of existing words in where the new combinations are very different, but somehow we figure out what is the intended meaning. Okay. So this notion of compositionality, which is really at the heart of what we're trying to achieve. The notion of compositionality, of course, is central in computer science, and already explains a lot of the generalization power of deep learning. So I wrote papers on this a few years ago. The very fact that we have distributed representations gives us a sort of exponential advantage, because you can generalize to new patterns, and there's an exponential number of these patterns. And there's another form of compositionality that comes up because of the depth, the number of layers in the deep net, which also gives an exponential advantage. But what we're talking about here with this systematic generalization of the kind we find in language is different. Maybe it's closer to something like being able to deal with analogies and closer to abstract reasoning. So that's the direction that many of us are now engaged in. If you're a baby, you need to be able to have that kind of out of distribution generalization ability, because the world changes all the time. Your body changes, you meet new people, you go to new places, and somehow you still have to make good predictions about the future. And so we may ask, how do humans manage to deal with those changes in distribution? And the answer from cognitive and neuroscience is, at least the best theory we have is that one of the important ingredients for this seems to be conscious processing. So if you remember, let me show this. I'm gonna go with the driving example. So if you're driving in your hometown and your usual path going from work to home or something, you can do this in automatic mode. Yeah, you can just not even have to focus too much on the road. You can talk to someone else at the same time as you're driving. I mean, probably you shouldn't, but the truth is you're able to do it. And instead, if you're driving in this new country where you drive on the left rather than on the right or something, you can do it, but you really need your conscious concentration on the situation, right? And when we do these things, we can only do one thing at a time. So when we do these kinds of conscious things, if somebody is talking to us, it really is disturbing, and we need our focus, our attention, right? So Dan Kahneman, who's a Nobel Prize winner, talked a lot about different kinds of tasks that humans seem to be able to perform that really fall into two very different categories. So there's the system 1 tasks and the system 2 tasks. The system 1 tasks are those you can do in a habitual way. You don't need to be conscious of what you're doing in the details. You can do these things very fast. They basically call upon your intuition. Most of perception is like this. You don't have access to how you recognize that this is a dog or a cat. So there is all of this implicit knowledge that is being called upon. That's system 1. And deep learning is very good at these things, the current deep learning. So what we want is to build deep learning that's good also at system 2 tasks, which for humans are much slower. If I ask you to add 31 and 43, you can do it in your head, but it's going to be so much slower than a calculator, right? Whereas your brain can recognize a dog so much faster and better than a calculator. So this is very different kind of computation. It's sequential. You go through steps in your mind, and then you can explain those steps to someone else. This is the way we program computers, right? Algorithms is system 2. A lot of the language has this nature as well. When we plan consciously, we are calling upon the same kind of skills. Reasoning, planning, all of these things seem to be belonging to a different category and belong more to the conscious realm. Okay, so this is what we're after. Like, how do we bring in the ability to do these things in neural nets? So one way to maybe get at the particularity of the system 2 capabilities is that it allows us to manipulate high-level semantic concepts, so the sort of concepts that you can communicate with language, in a way that they can be recombined on the fly, dynamically. And so you have this combinatorial possibility here that is, you can do it on the fly. That's important. That's how you adapt to new circumstances without having to retrain yourself for months, right? Whereas the skill, like the driving skill, that you can do without thinking, you actually need lots of training. Like, it's a slow training but fast execution, whereas the system 2 is almost no training is needed, or very little, and rather slow execution. Okay, and that calls upon a view of learning which maybe can give us some clues about how we can solve this problem. So a central idea in learning theory is that in order to learn, we need some a priori about what we're trying to learn. It can be very weak, but we do need to make some assumptions. And evolution has put these kinds of assumptions in us. Now, if we look at the system 1 and the system 2 kind of knowledge, so we are talking about two different kinds of knowledge. So the main difference is one kind of knowledge is essentially implicit and verbalizable and not verbalizable, whereas the other kind is explicit and verbalizable, okay? So an interesting question that I've been asking myself is, so we've already put in our machine learning systems a certain number of assumptions, like the architectures of these neural nets, that are good at capturing the implicit knowledge, the not verbalizable knowledge. But what about, what are the kind of assumptions that we could put in that would help machine learning deal with the system 2 task, deal with the verbalizable knowledge? And the good news is, because that knowledge is verbalizable, we actually know a lot about it, right? So in my group's research, we've tried to make a kind of list of assumptions that seem to work well for high-level semantic variables and how they're related to each other, that don't necessarily apply to low-level stuff like pixels and images. And so if we can put these kinds of assumptions in the way that we train our models, then hopefully we can enter the realm of system 2 machine learning successfully. So I'm gonna, in the say 15 minutes that are left to me, I'm going to give you some high-level examples of these things to make it a bit more concrete. So the first one that I thought about a few years ago is really something you can observe in language that is very different from in terms of the types of dependencies that variables have with each other. That is very different from if you look at pixels. Okay, so we're trying to see what kind of assumptions are relevant for high-level variables like words and language that are different from the kinds of assumptions you can make at the level of pixels in images, right? So low level versus high level. And one very striking property is that you can make statements about the world, probabilistic statements that involve, that have a high degree of certainty, so they are not vacuous, and involve very few variables, right? So if I say something like, if I drop the ball, it will fall on the ground, just a few words, just like, you know, less than a handful of concepts, and yet it's a very powerful statement. Like it will happen, like the probability that this is true is very high. Now you might think, well, yeah, sure, but what you have to realize is that you can't make that kind of statement at the level of pixels. Like if you're trying to predict one pixel given other pixels in an image, you actually have to look at thousands of other pixels in order to get a chance of, you know, making a good prediction for that particular pixel. So this is a very peculiar property of high-level semantic variables that we can observe in language. That means the joint distribution of these high-level variables has a structure that is very sparse. So that's the first thing. And then a second thing is more operational in some sense. So how do we exploit this sparsity, or how do we enforce this sparsity? Well, if you look at how humans seem to perform conscious processing, there's like a central ingredient to this. It's called attention. And until 2014, we didn't yet have really successful ways of putting attention mechanisms in neural nets. And so that year with my collaborators, we found a way to do that for machine translation, which turned out to be extremely successful. And the idea was to make, to use a gating, what we call a gating mechanism, where the information that flows from one group of neuron to another group of neuron is multiplied, is gated by some attention mechanism. So the attention mechanism controls how much attention is given to different pieces of information that are going to be sent to some group of neurons. And so in this way, it can select from a set. Now, this sounds like a very simple thing, but actually it completely changes the nature of what neural nets are doing. Like traditional neural nets are operating on vectors. Vector in, vector out, Each layer is just transforming vectors into vectors. But now we're talking about something different. We're talking about sets. So sets are not ordered. I mean, there could be implicitly some order, but the computation is invariant of the order. And sets can have arbitrary size, because I can put my attention, I can choose to attend to 1 out of 3 things, or I can choose to attend 1 out of 5 things, right? So it's very flexible. And we now have neural net architectures that uses these attention mechanisms, and they are incredibly successful. So it started with machine translation, as I said, but since then, pretty much all of NLP has been using these kinds of attention-based neural net architectures. The most well-known is the transformer that you may have heard of. Okay, let me go back to a particular more recent research that we've been doing to try to get at this notion of how do we decompose the knowledge about the different variables and the different pieces of knowledge appropriately, and how do we learn to decompose knowledge into these pieces. And so the first step here is to think of modular neural net architectures, where instead of having a homogeneous structure, we have all of these modules. Each of these modules is itself like a fully connected piece of network, but the modules are going to be talking to each other through a bottleneck of attention, which is similar to the bottleneck of attention that we find in human cognition. They are going to use attention to select what they want to use as input. Whether they're going to read their input from one module or another module, or from the outside input, so that sort of thing. And it has turned out that these kinds of architecture generalize out of distribution better than the standard homogeneous architectures. So as I said, this is inspired by work in the last few decades, the last 3 decades mostly, in cognitive neuroscience, where the taboo on the notion of consciousness has been lifted. I mean, not completely, but to a great part. And fortunately, people in AI now are starting to think of, okay, is this a word that we are allowed to use? Because, as I said, it looks like the way your brain is processing consciously is really different from the way that we're doing it unconsciously. And there is some utility to this. So if we understand better how humans do it, then that can really guide us into how to design AI systems that embody these ideas. And one of the central ideas in current theories, I mean, maybe the main theory of consciousness is called the global workspace theory, and the modern version, a global neural workspace theory, is that there is this bottleneck, right? So the attention mechanism selects an item that is going to be broadcast to everyone else. So all the modules are kind of listening. One of them is allowed to send information that's going to be your current thought. And then of course, you move on to the next thought and so on. And that gives rise to the sequential style of processing that we see in conscious processing. So one of the things we've done is to extend these modular architectures that I talked earlier, called recurrent independent mechanisms, to include specifically a bottleneck. So not only we use attention to communicate between the modules, but they have to go through this blackboard. And again, we find that we get even better generalization out of distribution using these kinds of architectures. I'm speeding up a little bit because I want to leave time for questions, but this is sort of the gist of this. And the last piece of work that I want to highlight is the work we've done on causal representations. So it turns out that one of the assumptions that's interesting about the high-level semantic variables is that they seem to talk about causality a lot. So if you look at the words in language, even the grammar, you have the standard construction, which is subject, verb, object. So this is actually a causal structure, right? The subject is typically an agent, like a person or an animal or something, the object is going to be the recipient of an action. So it's going to be the effect. And then there's the agent doing something, causing something to happen. And the verb is telling us what kind of action is going on. So it's this notion of causality is very important. Causality is also related to the notion of out of distribution or generalization. In fact, it's probably the best theoretical guideline to help us figure out how could we hope to meaningfully generalize to a new environment. Well, think of it like you move to a different country, but the laws of physics are the same. Human nature is the same. Culture may be different. The climate may be different. The laws of traffic may be different. But there are some fundamental things like the cause and effect relationships in the world have not really changed. So causality helps. I mean, if we understand the world in a causal way, we can probably be more robust to these changes in distribution. And in fact, we did show these kind of thing that you can train systems such that they will be more robust to changes in distribution, and then they tend to capture the causal structure. So the high level picture of what we're trying to do here is what we see on the right in a kind of schematic. So there's the low level like images and sounds. And your brain is somehow mapping that to a high level representation that captures the kind of concepts we communicate with language. So we call this mapping an encoder, and we're also able to go in the other direction. So we typically would have a decoder as well that can ground abstract concepts into concrete things, including low-level actions. And then at the high level, we have structure. We have the causal model that explains how one high-level variable can influence another one as a direct cause. And so the job we're trying to do here is to jointly learn about how to map low-level data to high-level variables, and how are these low-level variables connected to each other. So this is called causal discovery, right? Trying to discover the which is cause, which is effect, and what are the dependencies. So there's a lot of work in causality outside of machine learning, but it's fairly recent that machine learning researchers have started to think about how can we incorporate these ideas in machine learning systems. And one of the big issues is unlike in most of the work in causality that is in areas like economics or sociology or biology or medicine, where the high-level variables are known because these are the concepts that the scientists would be manipulating. If you want to build a robot, it has to somehow discover the right high-level representations. You can probably get clues from humans, but not everything will be given. So that's part of the challenge that's new. All right, let me skip.
Yoshua, you
yes.
can take 5 minutes more. We have some time.
Okay. Yeah. So let me mention that we've been deploying these ideas in a series of papers on discovering causal structure. But yeah, I don't think I need to go in much detail. Let me mention this paper, which is kind of interesting for people who think about programming. So remember at the beginning I said that programming is really a system 2 task, although we probably also exploit some system 1 intuition when we do that, but it's largely a system 2 task. And the way that we organize knowledge in programs may be also a good inspiration for our system 2 machine learning. And there's also actually inspiration from, again, cognitive science about how humans seem to be representing knowledge in generic ways. So up to that paper, the way that we were modularizing knowledge was aggregating in the same piece of neural net, both something like a rule or a schema that says how to do things with the values that function is applied to. Okay, so now you might see that in programming, especially if you think about object-oriented programming, we have a different picture. We have, say, methods that can be applied to many objects, right? So the class is a template for many objects, and all of these objects that are of the same class will be able to execute the same routines, the same methods. So in the context of these neural nets, how do we take these ideas there? Well, so the idea is the attention mechanism, instead of just selecting a module that's going to be executed next, or is going to do some operation, it jointly selects both the schema, which is sort of the computation that we want to do, like the method or the class, whatever you want to call it, and the object, like the actual instances, the variables that we want to operate on. So in the example here, what we see is, think of a video game, Pac-Man, where you have different characters, and at a particular moment, the character A is, executing the schema 1, and then maybe another one is executing schema 2, which is like a normal ghost, but at some point it may change and become a scared ghost, right? So now it has changed type, and it's executing different procedures. So this ability to decouple the computation from what it operates on, which seems trivial in programming, is something that attention mechanism allows us to do in neural nets. So what it means is that dynamically, the attention mechanism is learning what to call on what data at each step. That's a way to summarize this. So this is something we just submitted, and it seems to work quite well, and we are also extending in various directions. Okay, so let me start on my path to concluding. I've given you a kind of tour of some of the ideas that we're exploring to try to bring some capabilities to machine learning that seem to be currently missing. Capabilities that classical AI were trying to give to machines, and capabilities that humans have when they operate consciously. And in doing that, I have started to bring together a constellation of concepts that are not independent, that are related to each other. So remember, I started talking about out of distribution generalization, and the particular form of it we can see in language, the way we do it in language with what's called systematic generalization. And I've also talked about how this might be achieved by introducing a form of modularity and compositionality in the neural net architectures, so that on the fly, using attention mechanisms, we could pick out the right pieces, the right variables, the right rules, the right computations that need to go together, and sequence them appropriately. I've made the connection to causality, because this is in a way the underlying theoretical bedrock that allows us to think about how an agent can possibly generalize to a new distribution. Essentially, what we're saying here is the change in distribution is due to somebody doing something, which we call it intervention. So something has changed, right? So you moved to a different country. Somebody's, there's been an accident. Something has changed, and now the distribution that the agent is seeing is different. But if you can capture the way that the world works, that covers that change, you can make inference about that change, and you can adapt to that change in distribution, even though it might be a very big change in appearance. Like if I put on my dark glasses, everything in my vision is changed, but yet it's only one bit that's changed. It's the bit that says I put on my dark glasses. So at an abstract level, only one thing changed. At the low level, lots seems to have changed. So when we can learn to map the low-level stuff to the high-level stuff. And if we represent the causal structure at the high level, we have a chance to generalize out of distribution. Okay, so let me squeeze in a slide that is not really on the research I talked about, but maybe stepping back a bit on the social impact of what we're doing in AI research. As we are building gradually more powerful AI systems, what is happening? These tools are, being deployed in society. They're being deployed by companies mostly, and I think as scientists and engineers who are involved in these projects, we have a responsibility to be mindful of how those technologies are going to be deployed. Sometimes the problem is people may think too much of the capabilities of the machine. Like as I said at the beginning, we're very far from human level AI, and it's not ethical to use these machines in situations like killer robots or deciding whether somebody is going to have parole and other judicial decisions, where you really need to understand psychology, moral values. And we know that current machines are nowhere near understanding these things. We can't trust them for that, and it wouldn't be fair and just for humans to be governed by machines that are stupid like this. It would also be opening the door to discrimination, as has been shown. So we have to remember that AI is a tool made by humans for humans, and we have to think about, well, for what purpose, for whose benefit? Is it going to be used for positive social value, or is it going to be abused in some ways, or used to increase one's wealth or power versus the rest of society? So powerful tools can lead to concentration of power, and this is in contradiction with democratic values. So I think that there are a lot of people now around the world, and even hundreds of documents have been written to try to think about how we should use AI in society to make sure that these gradually more powerful tools are ruled by collective needs locally and internationally. So thanks very much for your attention.
Thank you, Yoshua, for this really enlightening talk. We have many questions, so we will pick some of these questions. I mentioned in the chat that people can vote for questions, and I will ask the most popular first. But I'm just starting by breaking this rule and ask one question that didn't get that many votes, the one by Michel Chaudron, but I guess this is for interest to our community. Could you speculate on the application of AI in software engineering? So in other words, how AI, this computation, AI-driven computation could be integrated or could be replaced, or the traditional software engineering?
Yeah, that's a very good question. So actually the work that I've been talking about has interesting connections to software engineering and programming in general. One of the things that current machine learning is not able to do is to program. At this stage, we are able to train a machine to program 3 lines of very simple programming language, and it will still make a lot of mistakes. So that ability to generate programs, to understand programs, is something humans are good at, but current AI, at least based on machine learning, isn't. And so what I'm hoping is, as we make progress on this system 2 path that I've been talking about, it will help us build systems that can understand software, and so find bugs, obviously, and other things that software engineers want to do. There's actually already people thinking about this. It's not something in the future, but it's going to take time. This is not a solved problem. I think that we are now seeing that we have at least some conceptual bases. I talked about the learning theory basis. I talked about the attention mechanisms, and the notion of out-of-distribution generalization and compositionality. We're starting to build those ingredients together. I see people, for example, exploring how to do theorem proving, which is sort of related to programming, using these techniques. But we're still like far from the goal. So you guys have jobs for a long time.
Good to hear that. The next question is from Andrzej Wazowski. The low-level representation of knowledge seems to be very statistical, whereas the conceptual level appears much more logical in nature, in the sense of classical logic. So when lifting towards the conceptual, are you considering switching to more logical representations? Will we be able one day to write prologue-like programs that will be executed on top of a lower level statistical perception machinery, say a deep learning network?
Yeah, so this view that is implicit in the question has been the view of many people trying to build neurosymbolic systems where the low level is kind of neural net, statistical, whatever, and the high level is logic and symbols. I don't think that's going to work. So I don't think it's even how it works in the brain. There are many reasons for this. One of them is we still need the high level to be learnable. And unfortunately, it's hard to learn in a purely symbolic frame, right? So you need soft things, right? You need probabilities, or you need the attention I talked about. I didn't explain it, but it's also soft attention. And your brain also has something like this. When it looks like you take a discrete decision, underlying it, we can see in your brain that they're competing alternatives that have a different trajectory, and eventually one of them wins. So there's a sort of winner take all. But before you get to that winning point, it's all continuous value. And from a learning perspective, this is a very useful thing to do. The other reason why I think it's more complicated than staking logic on top of stats is that one of the challenges with the purely logical approach or the classical AI is search. So search becomes exponentially expensive, or it's not clear how to do it well. And Prolog is trying to do it for us, but it doesn't scale very well. If you look at how humans are able to come up with good candidates for planning or solving problems that are logical, like theorem proving, it's very different from, we're not looking at a million different possibilities, right? So if you look at the way we are solving the problem in AlphaGo, which is a search problem essentially, you have this neural net that proposes candidates, and then they get evaluated in a way that you can think as logical, but you don't need a lot of candidates, right? And so a lot of the power here is in the system one part that's now helping the system two to do its job. So what I'm trying to say is that the integration of system one and system two is not going to be just you slap one on top of the other. It's going to be much more integrated and thus not as simple as we would have hoped.
Excellent. Related to this, a question by Brian Selick. Any thought on how do babies with no verbal skills yet deal with system two tasks?
That's a great question. There's a lot of inspiration to be obtained from researchers who are studying babies, child development, and pre-linguistic children are building up, for example, understanding of what we call intuitive physics. Like they start understanding gravity and things like this. Of course, way before they can understand or verbalize about physics. And so there's a lot that is going on in our causal understanding of the world, which happens either before language or before the linguistic capabilities allow us to talk about these aspects. And yeah, we don't know how babies do it, but clearly what it means is that babies are able to form these high-level conceptual representations like understanding gravity is my example, by themselves. It's completely unsupervised. Like nobody teaches them about gravity. And they don't seem to have it when they're born. It takes like a few months before they realize that there's this regularity that when you drop something, it falls. And so, yeah, this is very exciting yeah, and babies, as somebody read, babies just try. So that's another thing about babies that's really cool and inspiring for us is their ability to explore. Like they are the best knowledge acquisition machines in the world. They are incredibly efficient at trying, but not in a random way. It's actually very structured. There's a reason why they get bored. It's because they want to focus on the stuff that will allow them to learn faster. They don't have 100 years or 1,000 years. They only have a couple of years before they're going to be confronting, the other babies that are going to be nasty and so on. So they need to learn quickly.
Excellent. So our next question is from David Benavides. While working with the development of deep learning based systems, have you faced what we call variability explosion? Meaning that many parameters to configure that can change the feature of the deep learning based system? And if the answer is yes, how do you handle this problem?
Yeah. So we use a different word for this. So we call this hyperparameter optimization. But yeah, it's I don't think it's a big challenge for the community right now. You can easily parallelize that search, and there are tools to make that search fairly efficient, although we could probably improve in the future. So one of the papers I wrote more than a decade ago is showing that if you use almost any kind of random search, you can do much better than an exhaustive search, right? So in other words, you don't look at all the combinations, you randomly sample configurations, and from that you can extract information. And now there are much better techniques called Bayesian optimization and sequential model optimization that can do that, even more efficiently. But the main thing that has happened in the last decade or two is just that we have these parallel computing machines, GPUs, and clusters and so on that allow us to try 50 experiments in parallel, and usually that's enough.
Perhaps we will take 2-3 other quick questions, and then we will move to the break. So a question from Daniel Varro. What is the idea to tackle some subtleties known in traditional causal reasoning, like inconsistencies, contradiction, paradox? So
right.
how do you deal with that for this causal reasoning?
Well, the thing is, you go away from logic and symbols and you go into probability. So it's probabilistic causal reasoning that saves you. So now you can have rules that are inconsistent partially, sometimes, and that's not a problem. It's just that one way to think about it is they fight each other to find the most coherent interpretation, but it's not going to be a yes/no thing. It's going to be a probability. So this is how we deal with this. And humans do that all the time, right?
Excellent. Next question by Betty Cheng. How might software engineering and model-driven engineering, which is the topic of this conference, be applied to AI systems? Because usually we think about AI, how AI could help other disciplines, but could you think it the other way around? How software engineering and model-driven engineering could help or be applied to AI systems?
Well, I'm assuming you guys would know better than me the answer to this. So one of the things that has been an important driver of progress in our field is software. One of the first things we did in the early 2000s that really drove the field was to write very easy to use software for deep learning, at least the initial phase of deep learning. And we've seen this in other areas that it was very important. Now, the number of papers is like growing exponentially in this field, and it's becoming a zoo. I think having software engineers that can help us design more, a better trade-off between flexibility taking those pieces together in novel ways, which libraries and other say object-oriented frameworks can help with, as well as efficiency. So we are always in a tension between efficiency and flexibility in machine learning softwares, because our computations are expensive. They take time. Some experiments can run for weeks. So if it can be days instead of weeks, it's a huge difference for the research cycle. And when you deploy it in applications, it's a matter of dollars, or it's a matter of carbon footprint. I mean, the carbon footprint of the deep learning systems used by Google or Facebook is huge. And so anything we can do that can provide a better trade-off between efficiency and flexibility is going to be useful.
Next question by Bentley Oaks. So thank you very much for the talk. During the driving scenario, you mentioned that a new situation is painful, but we survive. It seems to me that this negative feedback is so much stronger than a generic utility function. So humans intuitively avoid things that hurt us or that we fear. Could a notion of pain or fear be useful for AI learning?
So it's already there in some simple ways. Reinforcement learning agents, for example, of the kind that we use to learn to play Go, of the kind that, for example, we are using now to learn to design new molecules. So there's a lot of applications of these deep reinforcement learning methods. They're driven by a reward signal that can be positive or negative, which you can simplistically interpret as pleasure and pain. One of the directions that researchers in this field are looking at is, instead of having a single scalar reward, having a broader variety of rewards. So think about emotions. What are emotions? There are really a rich palette of rewards or penalties that are triggered by specific social or physical contexts. And so there's interest in the field in enriching the things that the reinforcement learning agent is trying to predict to not just a single scalar, but a whole palette of things that might be analogous to emotions.
Excellent. Next question is by Edward. How do we internationally ensure the rules are followed? I guess he's referring to
to my last slide.
Yeah.
Yes. This is a tough one. I'm sitting on a committee on it's called a working group. It's called a Global Partnership on AI, which brings in about 15 countries. And hopefully this will grow to a larger number of countries, where we're trying to propose to governments actions that they can agree on in terms of coordinating their the way that they're going to be using AI. But for sure, there'll be dissent, and countries like the US, depending on the elections, of course, might stay out of the deal, for example. So I think, unfortunately, that the current international coordination tools that we have with the UN, OECD, and things like this are not appropriate. I don't think that they have enough strength to entice countries to play the good game of working for the collective benefits, say, of the environment, for example. So yeah, this is a hard problem. I think it's solvable, but the solution is going to be to change the rules of the game at the international level in some ways.
Perhaps we will take two last quick questions. So one question is by Eric Rabiser. How far are we from human level AI? Is this a goal at all? And if yes, is it reachable?
I'll start with the answerable questions. Yes, it's a goal. Yes, it's reachable if we don't destroy ourselves before then. And when? Well, I'm sorry, I don't have a crystal ball.
So perhaps the last question from the same person. A bit of a cheeky question. In your experience, how easy is it to understand, maintain software written by AI deep learning people?
Well, there's a big difference whether there are students or professionals. There's a lot of variability in student code, as you already know. And a lot of it gets thrown out. And that's why having these libraries and frameworks is so important. And that's where, as I said earlier, I think software engineering techniques to help us be better organized in the software that is being shared across the planet is certainly helpful.
But perhaps I'm mostly thinking about maintenance because because when you have like a AI based computation model in the system, so
Yeah.
how is it easy to maintain, to change, to update, because we have techniques for algorithmic software, I would say, but for this, so do we have to change it every time we want to have a new version, or this is incremental change? Or?
So the way it's done right now in industry, so this is where it's really deployed, is pretty brutal. They retrain the system from scratch, like each day, and then they run a battery of tests to see that it continues working on the old data. And if it's a big change, if there's been, it's not just retrained, but there's been changes in the algorithm, they run A/B testing, like for real, but on a small proportion of their users to make sure that nothing is broken. Because if it was broken, then only a few users will be impacted. So that's kind of the very brutal and expensive approach that is currently being deployed to kind of protect quality as those changes happen, both in the data and in the algorithms.
Okay, so thanks a lot, Yohsua, for this amazing talk and this question-answer session. So unfortunately, people cannot applaud because we are in a panel mode, but I guess people are all thanking you in the chat, and so thank you very much again, and
wow,
so we move to the break.
Thanks for your attention. Thanks for your question, and enjoy the rest of the conference.
Bye.
Bye.